Hi everyone, in this video we'll be covering the topic of pH and oxides. Looking at the learning outcomes, we'll be focusing on how pH relates to the concentration of H plus and OH minus ions, the use of universal indicator as well as understanding the pH scale. We will also be understanding the application of pH in soil pH regulation, and we are going to also look at the types of oxides based on their metallic and non-metallic character. pH is a concept that you probably have learnt about in lower secondary. And you have learned that the pH scale ranges from 0 to 14. That's where most of the substances actually fall within. If you go and read up a little bit more, actually pH can go beyond the 0 to 14 range. Okay, but just so that most of the things that we deal with on a day-to-day basis, they fall within the scale of 0 to 14. So based on the pH value, we will know whether something is acidic, alkaline, or neutral. And the value that is neutral will be a pH of 7. pH is actually a measure of the concentration of hydrogen ions. So the H actually stands for hydrogen in pH. So in chemistry, we use this short form with the square brackets to denote the term concentration. So when we put H plus in square brackets, we are referring to the concentration of H plus ions. pH is actually a mathematical term in which we can calculate it based on the concentration using this formula, negative log of the H plus ion concentration. This is not in your O-level syllabus, but I think it's interesting to note that there is a mathematical relationship between the concentration of H plus ions and the pH. What you need to take note over here is that when a solution is acidic, you have a greater concentration of H plus compared to OH minus. Okay? When the solution is neutral, your H plus and OH minus concentration are equal. And when the solution is alkaline, you have a greater concentration of OH minus compared to H plus. So this scale shows you the pH of different substances that you find in your everyday life and where they fall into in the pH scale. What is interesting to note is that the pH scale is not a linear scale. In fact, every pH value is a 10 times difference in the concentration of H plus ions. So a pH of 1 is actually 10 times more acidic than a pH of 2. So because we can't see H plus and OH minus ions, we use a chemical substance known as an indicator to tell how acidic or alkaline something is. So you'll be familiar with the litmus paper already, the red litmus paper and blue litmus paper respectively. We can also test the pH using universal indicator, which is a mixture of different indicators. You can actually get these pH test strips pretty easily. So if you want to test the substances at home, right, you just take one piece of paper and dip it in and you compare against the color chart to tell what the pH is. So over here is a list of other common indicators you will encounter when you do your practical. Okay, methyl orange, screen methyl orange, thymophthalate, and bromothymol blue. Right, this topic of acids and bases is actually very interesting. Okay, I have actually a lot that I can share with you, but I will just pick a few examples. One thing you can find very easily will be this thing called disappearing ink. Okay, so disappearing ink is a blue color substance, okay, which functions as an indicator as well. Disappearing ink is actually one of the indicators in this list here. Is actually thymophthalate. So I'm going to add an acid to my disappearing ink. Can you make a prediction what you think you will see? Okay, do you see that? It starts to disappear. Alright, so the blue solution turns colorless. So if the pH is high, it will be blue. And if the pH goes below 9, it will turn colorless. So how the ink disappears is by reacting with carbon dioxide in the air, which is acidic. And then it turns from blue to colorless. Then we have bromothymol blue that is commonly used in the aquarium to test the pH of the water, aquarium water. We can also more accurately determine pH using this pH meter or data logger with a pH sensor. Alright, here's another set of experiments that you can do in your free time. Okay, so I think you will probably have seen this before, quite common in Singapore, which is this butterfly pea flower. You can see? Yeah, so these are dried flowers, but they contain a very interesting indicator as well. So you can extract the indicator by adding hot water. Okay, let it steep for a while. Some people drink this as a tea. And you can then take this indicator and to test the pH of different substances you find at home. Okay, very easily, and has a very nice range of colors. This is one mini project that you can go back and try in your free time. I have some other suggestions that you can go and try. So I've shared the link with you. You can go and try some of these interesting experiments with indicators. One important application of pH is in agriculture. So depending on the type of crops you are growing, it is important to manage the pH of soil so that the crop that you are growing can grow optimally. So the pH of soil changes depending on which region of the world you are in because the composition of the soil is different. Also, some areas may be more affected by environmental issues such as acid rain, so on and so forth. To regulate the pH of soil is an important factor for consideration for farmers who are actually growing crops. You may have encountered this flower before. It's called hydrangea. Very interesting example where the flower blooms a different color depending on the pH of the soil. Okay, you can go and find out how it actually works, what's the mechanism behind this. All right, and this is the section that is very important in the learning outcome for this chapter. If the soil is too acidic, we can treat the soil with a chemical known as quicklime, calcium oxide, or slaked lime, calcium hydroxide. You'll recall that these two substances are alkalis and therefore they can neutralize the excess acids in the soil and increase the pH so that plants can grow more healthily. Most of the time the issue is with soils being too acidic because of using fertilizers, acid rain, or microbial activities. Okay, rarely do we have a situation where the soil is too alkaline. So the process of adding calcium oxide or calcium hydroxide to the soil is known as liming the soil. It's also important for farmers to add fertilizers to the soil, right? Many of the fertilizers are ammonium salts. Okay, one example is, let's say, ammonium sulfate. And why ammonium is because plants need three essential elements: nitrogen, phosphorus, and potassium for a healthy growth. And ammonium-based fertilizers provide the nitrogen that is necessary for healthy plant growth. And nitrogen, right, is an essential component of the chlorophyll in the leaves. So it's also important to add fertilizers to the soil. But then, you can never add fertilizers together with calcium hydroxide or calcium oxide. There is going to be a reaction. What kind of reaction will be happening? Are you able to make a guess? This is something that we have learned before. So the reaction is between an alkali and an ammonium salt. What do we produce? We produce salt, water, and ammonia gas. Why do you think this is a problem? What was the purpose of us adding the fertilizers in the first place? Is to provide nitrogen, right, for healthy plant growth. But what happens to the nitrogen now when you have lime in the soil together with the fertilizer? The nitrogen actually is lost to the surrounding as ammonia gas, and it defeats the purpose of adding fertilizers to the soil. Alright, so there is a reaction producing ammonia gas which escapes and resulting in the loss of nitrogen content in the soil, affecting the plant growth. Okay, so this is something that is not desirable. In this section, you'll be looking at a type of compound known as an oxide. An oxide is a compound of an element with oxygen. One example that you are familiar with would be carbon dioxide, like CO2. You are probably familiar with carbon dioxide in the form of dry ice. I'm going to show you a video now. We will first be adding universal indicator to water, followed by a few drops of an alkali. Now the universal indicator turns purple. When a piece of dry ice is dropped into the solution, observe the color changes. We observe that the indicator changes color from purple to blue to green to eventually yellow. This tells us that the pH is decreasing. What can you conclude about the properties of carbon dioxide? Carbon dioxide is an acidic oxide and therefore reacts with the alkali, bringing the pH down. Eventually, when all the alkali has been used up, we are left with a solution of carbon dioxide in water. When carbon dioxide dissolves in water, you actually form a solution of carbonic acid. Carbonic acid is a weak acid. It has a pH ranging between 4 to 5, and therefore the universal indicator turns yellow. Carbon dioxide is therefore classified as an acidic oxide. We can form oxides by combining metals with oxygen or non-metals with oxygen. In general, there are 4 kinds of oxides. The first kind will be your basic oxide. So basic oxides are oxides of metals and they are solids at room temperature. Metal oxides consist of a metal with oxygen, a non-metal, and therefore forms an ionic compound. Do you remember the properties of an ionic compound? Ionic compounds have a high melting point and therefore these oxides tend to be solids at room temperature. Of your metal oxides, we have also learned that they are bases. Some of them are soluble in water to form an alkali. Others are insoluble in water, however, they can still react with acids to form salt and water. So here are 2 examples. An example of a soluble basic oxide will be sodium oxide. An example of an insoluble basic oxide will be copper 2 oxide. So basic oxides, they can dissolve in water to form an alkaline solution, or they can react with acid to form salt and water as the only products. I will jump into the acidic oxide first. Acidic oxides are oxides of non-metals. Examples of acidic oxides are sulfur dioxide, sulfur trioxide, carbon dioxide, and phosphorus 5 oxide. These oxides are soluble in water. They can dissolve to form acidic solutions. Acidic oxides can also react with alkalis to form salt and water only. One example would be silicon dioxide, because silicon is a non-metal. Silicon dioxide reacts with sodium hydroxide to form this salt known as sodium silicate. Carbon dioxide reacts with sodium hydroxide to form sodium carbonate. There is a group of oxides known as amphoteric oxides which have properties of both acidic and basic oxides. These are metal oxides that can react with both acids and bases to form salt and water only. In other words, undergo the neutralization reaction. The word amphoteric is similar to when we say someone is ambidextrous, able to write with his left and right hand, or amphibian, can live on land and in water. So amphoteric meaning it has both properties of acids and bases. Zinc oxide is one such example. So zinc oxide behaves as a base, reacting with an acid, hydrochloric acid, to form the salt zinc chloride and water. What's interesting is that zinc oxide can also react with an alkali. So over here, zinc oxide is behaving as an acid, reacting with an alkali or base to form the salt sodium zincate. The 3 amphoteric oxides are your zinc oxide, aluminium oxide, and lead 2 oxide. Finally, neutral oxides are oxides that have neither acidic nor basic properties. And the 3 examples are water, carbon monoxide, and nitrogen monoxide. If you find this table too much to manage, just remember 2 simple rules. Rule number 1. As long as it is a metal oxide, it is basic in nature, except oxides of zinc, aluminium, and lead, which are amphoteric. Rule number 2. Non-metal oxides are acidic, except for 3 examples, CONOH2O, which are neutral. So I'll now present you with a list of different oxides. Let's put what we have learned into practice. Can you classify each of them into either acidic, basic, amphoteric, or neutral? Pause the video and have a go at it. So these are our acidic oxides. They are oxides of non-metals. These are our basic oxides, oxides of metals. These are our 3 amphoteric oxides, zinc, aluminium, and lead. And these are our 3 neutral oxides, CONOH2O. Let's go back and review the learning outcomes. We have discussed that the pH is a measure of the relative H plus and OH minus concentration. We have looked at universal indicator and the colors of it at different pH. We have also looked a little bit deeper into the pH scale, which ranges from 0 to 14. We have learned the importance of how to control the pH of soil by adding calcium hydroxide, which neutralizes the excess acids in the soil, bringing up the pH. We have also learned how to classify oxides based on acidic, basic, amphoteric, or neutral, based on whether they are oxides of metals or non-metals. So that's all for this video. I'll see you all in class.